Well, suppose that choices are not uniform. So you have an excess demand correspondence. Which we should denote by the usual large Z. These correspondence associated with every price system a set of excess demand vectors, as before. Let's suppose that this Z is upper heavy continuous. A property which is simply a generalization of the usual continuity for a function. You encounter this property in the first part of the course with reference to the budget correspondence, the demand correspondence, and so on. Moreover, Z as ZOP is non-empty, so it's always an excess demand vector, compact and convex. All the properties which are required by Capitani's fixed point theorem. Given all these assumptions, and the usual strict variance law, of course, every element of ZOP multiplied by P gives 0 as a null value. Given all these assumptions, we shall prove the existence of a P star in delta and the existence of a Z star in Z of P star such that Z star has all non-positive components, a free disposal equilibrium, in the case of a correspondence of a chords. This is our thesis, to prove the existence of equilibrium in the case of a correspondence. The theorem is proved by means of a preliminary lemma, from which our result can be obtained immediately. The lemma is this. Given all these properties, there exists a P star in delta. There exists a Z star in Z of P star such that for every P in delta, P times Z star is less or equal to 0. This is our preliminary lemma. There exists a price system, there is a vector of excessive demand, such that when evaluated with respect to any other price system, this vector has a non-positive value. When you succeed in proving this lemma, our theorem, as we shall see afterwards, follows almost immediately. So, let us prove this preliminary lemma. First result is the following. Since for every P, Z of P is a compact set, the set Z and Z is a upper and continuous correspondence. The total image of delta by means of Z is likewise a compact set. This is a well-known theorem about upper and continuity. Since delta is compact, obviously, and Z is upper and continuous, then, and every Z of P is compact, then also the union of all these Z of P is a compact theorem. Cosa sono scritto? Is a compact set, sorry. Is a compact set. Let us represent this result by means of a graphic. Suppose there are only two goods or codes, good 1 and good 2. Take any price system. This line is simply the set of all the vectors which has a null value with respect to that price system. By strict variance law, the set Z of P lies entirely on this line. Because by strict variance law, every excess demand vector has a null value according to P. Repeat the same construction by any other price system. For example, this is another price system, you obtain another, say, Z of P prime, and so on. The union of all these sets, which is the image by large Z of a unit simplex, is a compact set. If you unite all the images of P by means of Z, you obtain another compact set. This is the graphical representation of this result. Z of D is the image by means of Z of the entire set D. In other terms, the union of the single images relative to the different price system. And this set must be a compact set by the compactness of delta, the compactness of each Z of P, and the upper and continuity of the correspondence Z. So you have this set, Z of P, of delta. I repeat, it is a compact set. The form of this set is very strange, and is the generalization of a price quantity function of elementary consumption theory. However, this set is not, while compact, is not necessarily convex. But we can convexify it by passing to its convex hull. To its convex hull. And since Z of delta is compact, by the theorem we previously quoted, also the convex hull of Z of delta is a compact set. I am simply applying our previous theorem on compactness of a convex hull of a set, which is compact. Is it clear? I repeat. Start from any element P in delta. This is the image, the set of excess demand vectors. When you change P, clearly the set changes. Define the union of all these images when P ranges in delta. You obtain Z of delta. By our assumption, this Z of delta is a compact set. And by our previous theorem of a convex hull, also the convex hull of a compact set is a compact set. You obtain in the end a compact set. Is it clear? Now, we can cancel. This theorem is in reality much more difficult than the previous one. Well, now, in order to prove the existence of equilibrium, following Debray, which is the original author of this theorem, we must introduce a fictitious agent, which can be identified with the variation actionier. So, also in this case, we return to Varras, to the original setting by Varras. Before we reintroduced the tâtonnement. Here we are introducing the actionier as a fictitious agent. In other terms of economy, whereas H consumer, F firms plus this fictitious agent, the auctioneer, whose task is simply to adjust prices. The choice set of this auctioneer is nothing but delta. Let us see in which way the auctioneer works. Take any Z which belongs to co of large Z of A, the set we previously defined, which is a compact set. This is a vector of excess of demand. It has some positive, some negative components. Well, but attention, the auctioneer associated with this vector Z, the set large F of Z, which is constituted by all the price system in delta, such that with that price system, the value Z is maximized with respect to every other element of delta. Is it clear? Take any excess demand vector, generalized excess demand vector, of course, because here we are considering the convex hull of effective image of, sorry, this is that, of image of excess demand correspondence. Oh, well, this can be interpreted as an excess demand vector with some positive, some negative components, some null components, and so on. The auctioneer associated with this vector Z, the set of the price systems, P in delta, which maximize the value of Z with respect to every other element of delta. Suppose, in the simplest case, that Z has this form, say, plus 2 minus 3. What is an element of F of Z? It is clearly this price system, 1, 0. Because when you multiply P times Z, you obtain 1 times 2, 2. Plus 0 times minus 3, 0. You obtain 2. If you choose any other price system in the simplex, the value is less. And so the solution of this problem of maximization in this case the only element of f of z, is this price system. In other terms, the auctioneer chooses the price system in order to maximize the value of excess demand vector. But this is an extreme form of tâtonnement, because remember, the Varrogian auctioneer increases the price of the goods for which there is a positive excess of demand and decreases the prices for which there is a negative excess of demand. But by this change in prices, he increases the value of original vector. In this case, the auctioneer maximizes this value. So, this behavior of the auctioneer is nothing but an extreme form of tâtonnement. Let us return to our previous example. Plus 2 minus 3. And suppose that the price system according to which z is chosen is suppose that in the traditional context of Varras, when the prices are 3/5 and 2/5, this is the excess of demand vector. The value of this vector is 0, clearly. So, strict Varras law is verified. The Varrogian auctioneer increases the price of the first good, the good which has a positive excess of demand, and decreases the price of the second good, the good for which there is a negative excess of demand. In this way, he increases the value of Z. Is it clear? Because in the inner product, the price of a good for which there is a positive excess of demand is increased, so the product is increased. While the price of a good for which there is a negative excess of demand is decreased, so the product, the value of the second component is increased as well. So the total value of Z increases when the prices are adjusted. The Debre's auctioneer behaves in a similar manner, but in an extreme manner. It maximizes the value of Z by suitably choosing the price system. And the maximized price system is 1, 0 as before. Well, substantially, we must demonstrate that this correspondence F is apparently continuous. When the proof of apparently continuous is given, the theorem follows almost immediately. So let us have another break, and then we should prove the most difficult part of this proposition.